Welcome to this lecture on stacks. In this lecture, we'll talk about an overview of stacks briefly, and then we'll talk about implementing stacks with linked lists and arrays, and do analysis of this as we go. So stacks, of course, use last in, first out, or LIFO order. So the only thing that the most plain type of stack supports is access to the top of the stack. You can push to the top, you can pop from the top, but you can't do anything any further down. And we've used stacks already many places in this course, just within the first few weeks. In Project Zero, we had function call verification, where we pushed each function call and we matched each function return and popped those off. And we also used stacks to implement depth first search to keep track of the path in a maze and allow for backtracking. And we'll see other applications of stacks in a couple of lectures. So let's just dive right in, and we'll talk about what if we implemented a stack with a linked list. Here's what it might look like over here. We have a top pointer, right, which points to a node, which points to the next node, and so on until we get to the end of this linked list, which is signified by the next being null. Now, if we wanted to implement the methods get the top, push, pop, and is it empty, these are pretty simple to do with a linked list. The empty, of course, just checks to see, is the top pointer null? And if it is, then the stack is empty. And if it's not null, then the stack is not empty. And of course, all that involves doing is looking at the top pointer and checking it for null. So that costs us order one time. It doesn't matter how many items are in the stack already, it still costs us order one time. So that's nice. Let's talk about popping the stack. Let's go this way, I guess. Actually, let's talk about getting the top. Getting the top of the stack requires looking at the top element, the top pointer, right? This is the method. This is the data member. They're the same name. Getting the top of the stack just requires going to the top pointer, following it to this node, and returning what it's pointing to, right? It doesn't matter how many things are on the stack below here, right? So that's also obviously constant time, because we just have to do a fixed number of things. We just have to dereference the stack, essentially. Let's look at push then. Suppose that I wanted to push something onto the stack. It's going to go onto the top, so we're going to have to do a few steps. The first thing is to allocate a new node. By the way, you'll notice, I always like to say that you'll notice that I've drawn this linked list vertically up and down, because stacks are vertical, lists are horizontal, like we saw in the last lecture. All right, so in order to push onto the stack, I create the new node. Let's create a temporary pointer P, which points to that node that we've just created. We created it on the heap, of course, using new. And then we're going to make its next pointer point to what top was pointing to, or is pointing to. And then we're going to change the pointer for top to point to that new node, right? And in order to do those steps, we had to allocate the node, make it point to what was the top, and then make the top pointer point to it. Doesn't matter how many things are in our stack, it just requires those few operations. So pushing requires constant time. Okay. Now, if we were to pop from this stack, we would then need to, again, go to the top, follow the pointer to what it's pointing to, and then create a temporary pointer to hold that node so that we can delete it later. Then we'll make the top pointer point to what that node's pointing to. So in other words, we're going to make it point here. And then we need to null out this pointer so that we don't have some sort of cascading delete. In other words, if we delete this node, we don't want its destructor to possibly delete the next node, which would possibly delete the next node. We're just trying to remove one here, not all of them. So we'll null out this next pointer by setting it to null. And we can do that safely now because top points to that node, and then we can deallocate it, right? So those few steps that we had to do, we had to change top's pointer, we had to null out this pointer, and then we had to deallocate it. Doesn't vary depending on how many items are in the stack. So again, this is constant time. So we can do all of the operations for a stack: push, pop, get the top, and figure out if it's empty in constant time. Before I move on, though, to the array-based stack, I want to do a thought experiment. Could we put top at the other end? And the other end meaning down here. Could we put top down here? What do you think? I always like to pose this idea. Well, if we're using a singly linked list, let's see. Could we get the top easily? Yes, we could still get the top easily. Could we push easily? Yes, we could still push easily. We'd create the node, right? Make it point to what top, make top's next point to it, right? So this would no longer be null. This would point here, and then make top point to that new node, right? So that would still be constant time. How could we pop though? Well, if we have a pointer, again, let's go back here. If we have a pointer to this node, we somehow want to get rid of that one and make top point up here. But how do we do that? We actually don't have a way of doing that. There's no way to go through the top to get to any other node except for the top. So pop doesn't work at all if we were to put the top at the other end. Okay, so just make sure that when you're using a linked list for a stack, you're doing it in the right order. All right, let's talk about an array-based stack. Here, we've got this array. Again, it's going vertically because this is a stack. Of course, that's not true, right? The orientation of how I've drawn this makes no difference. But let's think about what data members do I need to implement a stack, an array-based stack? Well, I need the array itself. I need to know its capacity, and I need to know where its top is. So right now, the top would be at equals 0, right? Which would essentially, it's not a pointer, it's an integer, but it would essentially point to index 0, okay? So when the top is equal to 0, then if I want to, say, push onto the top, I would go to top and I would put something there and then increment the top. So top really actually refers to one past the item in question. I wouldn't really want to start with top equal to -1. It's more common to start with the top being 1 above, or in this case 1 below, where the last valid element is. And this might seem strange, but it's kind of like how in the standard template library, the end iterator is 1 past the last valid element, okay? So how much time does it take me to push an element onto the stack? Well, I can do so in constant time. Why is that? Well, because I just have to increment the top and put something there, right? Increment the top and put something where top was. So that's constant time. What about popping from the stack? Well, all I have to do is decrement the top, right? If I decrement the top, then essentially this item goes away. It's still there, right? The bits are all still there, but what I treat as the top is now this item and not this item. So pop is also constant time. Constant time with respect to how many things are in the stack. And what about getting the top? Well, I have to, if the top is at 2, then really the last item is at 1, so I have to go to top -1, but I can do that in constant time because I have random access using an array. And determining if the stack is empty, well, this is where the top being the one past the last valid element makes more sense. The stack is empty if top is equal to 0, so I can check that in constant time as well. Okay, so implementing an array-based stack is also very simple, and if it gets full, I can just double its capacity, move the items over, and then delete the old array. So here's a summary of the analysis of the list and the stack implemented as a linked list or as an array. So here we have list, list, stack, stack as a linked list, array, linked list, array. And what you'll notice here, all of the stack methods are constant time, regardless of the implementation. But not all of the linked list, the list implementations are constant time. We have these order n operations for random access and for adding or removing to the middle of an array-based list, okay? And I've made some notes down here that we're showing the worst case behavior. We talked last time about how a linked list-based list does better with linear access rather than random access, and array-based lists do better, are more efficient with add and remove at the back or the end of the list, Okay, but if we're doing that, then a stack might be more appropriate. All right. So sometimes the implementation does matter, like in the case of a list. Sometimes the implementation doesn't matter, right? Asymptotically speaking, I could use a linked list or an array for a stack and get constant time access for all of these important operations that I need to support. Does that mean that the list and this array are equally fast? Not in practice, no. Which one is actually faster depends on your implementation, depends on your computer, depends on how large your stack is. Um, and of course, with the linked list, we're wasting a little bit more memory than we might with an array that's completely full. In general, I would say that the array-based stack is probably going to be faster, but if you're really highly constrained on wanting to make sure that you don't use up a huge chunk of memory and you have a huge stack, a linked list might make sense because it can use up sort of different corners of memory. It doesn't have to have a big contiguous portion of memory. So next time we'll take this same type of analysis, but for queues.